whenever I run the simulation, when I check under the total deformation, one of the arches disappears. It doesn't do that on the equivalent stress or strain, but it hasn't mattered what loading I put on it, but it just disappears.
Yeah. Okay. Let's go ahead and so what right now the it's only showing the deformation for two of the faces, so it's only doing it for the road and because normally like you click on the equivalent stress right here. This does it for all bodies, and so I think you might have had those two selected when you created that total deformation.
Okay.
And so if you, I actually don't know how to change it from here. Actually, so usually what I do is I just delete it.
Gotcha. Well, I've been struggling with that for a while. Just trying to figure out, I don't get why.
It actually took me like a long time to figure that out.
Okay, all bodies.
And you don't have to run it again. So if you right click on solution A6, you can just say evaluate all results.
Oh, that's good to
And
know.
then it's a lot faster. Yep. There you go. Yep.
Awesome.
It took me like over a year of learning Ansys to figure this out. Sometimes it would happen to me too. What the heck is going on? And then I realized that.
Well, now I'll know to look at geometry and see if I must have accidentally had like those two sides selected and not this one.
Yeah, I feel like that's the cause of a lot of random Ansys errors. It's having certain things selected and then you create something.
And then just not knowing where to look to kind of diagnose.
There's so many things to look at in Ansys.
And then
I'm still learning stuff every day.
I ended up doing like a pressure of 1 PSI in the middle. Is that kind of the appropriate? I think I ended up with the equivalent stress of like 315, so a little bit less than the yield strength.
Okay.
So, okay. Thank you very much.
Yep.
How's it going, Dr. Tran?
Good. Yeah, excited to fly. I haven't flown in a while.
My first, your wedding this weekend, right?
Yeah, probably my first and only time in Columbus, Ohio. My fiance and I were talking. I don't think we'd ever have a reason to go back to Columbus, Ohio after this. So we're going to make the most of it.
And enjoy all two of their buildings.
Have you been there before?
No, I haven't, but I'm assuming that that's probably the closest landmarks they probably have. I don't know. I don't go out as much.
That's my impression too.
Question, is today going to be an Ansys day or no?
No, so we're not going to see answers for a while actually, and so we've done the first 4 activities, which is kind of what I consider kind of the essentials of Ansys. Really, the first 3 are kind of like that, and then we're going to take some time to do some theory, and then after we take the midterm exam, then we're going to pick up the Ansys activities again after that.
All right, cool.
Mm-hmm.
Oh, Professor?
Yep.
Can I ask you a question?
Sure. So.
Okay, so when I was trying to do the meshing for the activity.
Yep.
I'm not getting an error, but it's not giving me the green check mark. The only thing I could think of is that one side, just when you zoom in, a very, very small gap. Is that the reason? For like the truss and the road, where the truss and the road meet?
You should still be able to mesh it even if there's a gap. Are all the parts of your geometry, do they have the green check mark next to it?
Yeah.
Okay.
Let me just double check just to make sure.
Because there is one kind of rogue part that that you have to suppress, and that might be preventing it from meshing. But
yeah, I had a similar issue. I was able to find it. Apparently, the top bar for the bridge, it was clipping through onto the frame, and apparently that was giving me issues. So I kind of put that in my report as to why I couldn't get the simulation working.
Okay.
At least from the solid model part.
I see. Okay.
I think I'll try that because I did what you say by like having the road within the beams or something.
Mm.
Yeah. Okay. Thank you.
All right, it's 5:30, so let's go and get started. All right, good evening, everyone. How's everyone doing today?
Pretty good, Professor.
right.
Pretty good.
I'm good. I'm good. Yeah, hanging in there. I think as all of you guys are, I know. I know this part of the semester is always really busy. So I always appreciate you guys coming out to the lecture. So especially this semester because they're recorded. So I know you can always just watch them on your own time. So for those of you who come out, it means a lot to me. So thank you for that. Right. Okay, so the plan for today is we're going to continue with our lecture notes on truss elements. We'll see how far we can get. I'm hoping that we can finish today, but it's quite a tall order. But no worries. We'll get as far as we can, and then we'll go from there. Okay. I'm working on your guys' next homework assignment, which is going to be a written assignment. Okay. It's not an ANSYS activity, and so it's going to be practice with all of the truss and springs. And next week we're going to go over beam elements as well. Okay. It is quite the doozy. So I've been working on it all day today, and I really want to get it out to you before I leave for my trip. And I've been kind of working on it all day. So I think and probably among all the homework assignments I've created since working here, this is probably going to be one of the longest. So I'm going to give you guys 3 weeks to work on it. You know, and it's going to be due basically right before the midterm. So definitely start on it. You can't do everything on the homework assignment yet because we have to cover beam stuff next week. But you should be able to do, you know, after today, you should be able to do about 65-70% of it. So definitely take a look. Actually, maybe the week after, because it's I know next week the midterms projects due. So you know, I know you guys will be working on that. But you know, I did want to get that out before the weekend. Okay. All right. So I think that's it for announcements. And so are there any questions I can answer before we get started? Okay. All right. When is the midterm scheduled? So right now the midterm was supposed to be scheduled for I think, let's see, we're in week 9 right now. Next week is week 10. It was supposed to be for the beginning of week 12, and so it was going to be pretty soon after the midterm project was due. But since that was pushed back, then I think I'll probably push back the midterm by at least a week. And so I'm thinking probably beginning of week 13. That's probably what I'm thinking right now. So a little bit less than a month from now. Yeah. Mm-hmm. Yep. Yeah, I'll have the exact date. You know, I'll get the exact date to you guys once I really plan it. But you know, technically this class is supposed to be in person, and so the midterm exam will take place in the classroom, and so that is going to be the one day this semester where I do require everyone to be in the classroom to take the exam. So there's not going to be the exam won't be online at all. So you need to come to the classroom for that. Okay. But we'll talk about that more, you know, as we get closer to the exam, but, you know, just want to make you guys aware of it. Okay? All right. And so let's go ahead and keep going with our lecture notes. Okay. And what we were talking about was direct stiffness problems in 2D. Okay. Or more specifically for right now, we're doing truss problems in 2D. Because we've done basically almost everything we can in 1D with regards to springs and trusses, and so now the next step is to move it up to 2D. Okay, and by 2D, what I mean is, you know, we're going to consider cases where, you know, we're going to tilt our truss element up like that. Okay, and so let's say that we have an angle theta right there. Okay, and our truss is going to go up like that. Okay. And the big difference that what you'll see is that instead of just computing one component of displacement at the end nodes, what we're going to consider instead is 2D displacement. Okay. And so if we call this node 1 down here and node 2 up here, then we're going to have a U1x, a U1y, a U2x, and a U2y. Okay. And so our element stiffness matrix is going to grow, as well as the number of unknowns that we have to solve for in 2D is going to grow as well, because we have to solve for each component of the deformation. Okay. And so to do this, you know, we're basically trying to make a transformation in between what's known as the local coordinates to the element and the stationary coordinates. Okay. Right. So remember the difference between these is if we have like a vector like this. Okay. And this vector could represent the direction of a truss element. The local coordinates would be defined, you know, along the lines of that vector. Okay. Okay. So let's say we have an x hat and a y hat. Okay. Whereas the stationary coordinates, they would be defined in terms of, you know, just the classical x, y, you know, vertical and horizontal that we usually do. Okay. Right. Just like that. And so we need a transformation in between these two coordinate systems in order so that we can form the element stiffness matrix of our 2D truss elements. Okay. Okay. And we were just kind of in the middle of defining that transformation. All right. And so that's just a little bit of a recap of kind of where we've been and kind of where we're going. So any questions on this so far? Okay. All right. And so let's go ahead and start deriving that transformation. Okay. And so what we said was that we have this relationship right here, right? Where we have, let's say we have an arbitrary vector u, and in here on the left side, we're defining that vector u in terms of the stationary coordinates. Okay. And then on the right side, we're going to define that same vector u, but in terms of the local coordinates. Okay. And remember, I give a hat to all the local coordinates. Okay. Okay. These two expressions have to be equal to each other because it's the same vector. We're just kind of defining it or describing it in terms of different coordinate systems. Okay. And so what we ideally would want is, let's play with this expression a little bit. And in particular, let's solve for different expressions for the unit vectors in the stationary coordinates such that we can form this relationship. Okay. And so let's start with the unit vector I, which remember is the unit vector in the horizontal direction. Okay. Let's define this in terms of I hat and j hat. All right. And so let me start by drawing a unit vector I, okay? Right, so unit vector I is just perfectly horizontal, right? Because it's a unit vector in the stationary x direction. And then now I'm going to draw in the components of this vector in the local coordinates, okay? And so remember, we're going to assume that our local coordinates are going to be rotated by an amount theta, okay? And so this direction right here that I've drawn in red, this is in the I hat direction. Okay. And then I'm going to draw a line perpendicular to that. Okay. And this is going to be in the j hat direction. Okay. Right. And so what we have here is we have basically a right triangle where the only angle that we know, or I guess we know all the angles, but the angle that we're going to define this by is the rotation angle, which is the angle that we rotated from to get into this local coordinates. Okay. All right. And so let's define the lengths of these sides. Okay. Okay. And so for that near side, what we have is a length of I magnitude, which is the length of the hypotenuse of this triangle multiplied by cosine theta, right? Right. And then for the longer side, or the side that appears longer here, that length is going to be I sine theta, right? Right. And so this I cosine theta is the length of this side, and this I sine theta is the length of that side. Okay. Since the I here is a unit vector, then remember a unit vector has a length of 1, and so we're going to go ahead and cross these out and turn them into 1. Okay. And so with that, we get the length of this side is cosine theta and sine theta. Okay. And at this point, I'll remind you that this is in the I hat direction, and so this is basically the same as cosine theta I hat, and then this this side right here is in the j hat direction. Okay, and so if we multiply that by the j hat vector, we get sine theta j hat. Okay. All right, and so what we can do now is we can put this together, and if we define this unit vector I without the hat in terms of these two directions, what we can say is I is equal to I as a vector is equal to cosine theta I hat minus sine theta j hat. Okay. I put a minus in front of the sine theta because this is going in the minus j hat direction. Okay. Okay. And so here we have our first relationship where we have I hat, or the regular I, in terms of I hat and j hat. And so what we can do from here is we can take this and plug it into this expression right here. Okay. And then that's going to eliminate one of the unknowns in that equation. Okay. And so what I'm going to do on the next page is I'm going to do the same thing, but for j. Okay. And so I'm going to form a triangle which puts the j in terms of I hat and j hat, and then we'll form an equivalence relation from that as well. All right. Any questions on this?
Yeah, quick question.
Mm-hmm.
So you broke down I into component form in terms of local coordinates?
Exactly. Yep. Mm-hmm.
Okay.
Mm-hmm. Yeah. So basically our goal right now is that we have this equivalence expression up here, and we want to eliminate both the unit vectors in the stationary coordinates. So we're going to put everything in terms of the local coordinate unit vectors. Yeah. Mm-hmm.
And one more question.
Sure. Mm-hmm. No problem.
So then the j hat is technically negative because the vector is pointing this way, and if you were to rotate it, kind of like
Yeah. Yeah.
if you were to rotate it kind of like that, it'd be pointing down.
Exactly. Yeah. Mm-hmm. Yeah. So I think it's probably best visualized from this image right here. And so we drew when we drew this side of the triangle right here, right, we were going basically and because this angle theta is kind of the same as this angle theta right here, right? And so when we drew the short side of the triangle, we went kind of up and to the right. And so you can see up and to the right is in the positive I hat direction. And then when we drew the other side of the triangle in the j hat direction, we went down and to the right, right? And so if we go back to the other page, then if we go down to the right, that's in the minus j hat direction from that. Yeah. Mm-hmm. Yeah, it's a little bit hard to visualize. So, definitely kind of go back and forth between these slides just to kind of understand what we're doing. All right, and so let's do the same thing, but for the the I vector. Okay, I mean the j vector. I'm sorry. Okay. Okay, and so j vector. Actually, let me draw it over here. J vector goes vertically up. Okay. And then once again, we're going to break this down into a vector that goes in the I hat direction. Okay. And so the I hat direction goes this way. Let me draw this in red. Okay. Okay. So I hat direction goes that way. And then we also going to break it up into another one, j hat component, which is that way. Okay. And the angle that we rotate on is this one right here. Okay. All right. And so if we form the same kind of relationship, so we say that the j vector is going to be equal to a component in the I hat direction. And so this component here is this one right here. And so this is going to be sine theta I hat. Okay. And it's in the positive I hat direction because it's going up and to the right, right? And then we have a component in the j hat direction. And in this case, it's going to be a positive cosine theta j hat. Okay. It's positive because it's going up and to the left, which is in the positive j hat direction. Okay. All right.
When is it negative? So for the cosine, if it's going to the up and left.
So for the j hat one, we're in the negative direction if we're going down and to the right, right? Because if we let me draw it right here again. So if we take our coordinate system and rotate it by an angle theta, then it looks like this, right? And so this is the positive I hat direction. This is the positive j hat direction. And so we would have a negative. Our j hat component would be negative if the vector was going in the opposite direction. Right? And so if our j hat vector here was going down and to the right, that would be a negative component here, right? And then for the negative I hat component, the vector would have to be going down and to the left.
Okay, I see. Thank you.
Mm-hmm. All right, so let's go ahead and plug in for these expressions.
Excuse me.
Yep. Mm-hmm.
Do you just define like arbitrarily, like choose the direction of these I hat and j hat, or you just choose them in order to make like a so like I plus j equals I hat plus j has. You're just doing it this way so that the addition would be vector addition would be equal to I, or in the j would be I hat. There's like some triangular rule in, I think it's like in vector algebra. I don't know.
Yeah. So the directions of the local coordinates are defined by the rotation that we do, right? So if you imagine that we always start here, right? And so this is classical XY, which is in the horizontal and vertical direction. If we take this entire system and we rotate it, right? And so we rotate it this way, right? And so we rotate by an angle theta, then we end up with the local coordinates in those directions, like right that. Yeah. And so their directions are basically starting from neutral, and then we just rotate from whatever we want to. So like imagine a clock that's at 3 o'clock and noon, and then you rotate kind of the whole thing. And those are the directions of the positive axes. Okay.
Yeah, it does. But what I'm saying is just when you're just calculating I in terms of I hat and j hat, your j is basically in the opposite direction of what we just calculated with this theta thing. So basically when we're just like rotating it with a theta, it's basically like that. But then here, the j that you're defining is like this way and like that. It's just basically in the opposite direction. So never mind. Yeah.
So we're using the rules of vector summations here, right? And so we are the vector that we want to end up with is this horizontal one right here. And so when we add together a vector in the I hat direction, right? And so if you go in the I hat direction, we have to go this way, right? Let me do it over here actually. And so we have a horizontal vector right here, right? And so when we add our two vectors, we have to end up right here, right? And so we're starting here on the left, and we have to end up right here on the right. And so when we first we go in the positive I hat direction, and so we go that way, right? And then in order to get here, we have to go down this way, right? And so that's why we have these two vectors right here. Yeah. It's because we always have to end up at the positive I. Yeah. All right. Okay, so let's go ahead and plug these in. Okay. Because remember, the goal for this was to basically plug them into this expression right here, okay, with all the ux's here. Right, and so let's plug in to that expression. And so we have ux, okay, and we plug in for I. From the previous page, we get ux times cosine theta I hat minus sine theta j hat, okay, plus uy, and we plug in for j, which is what we have up here. So we have sine theta I hat plus cosine theta j hat, okay. And this is all equal to ux hat I hat plus uy hat j hat. Okay. And so now I'm going to rearrange this left-hand side so that I have terms of I hat and j hat. Okay. Okay. And so if I do that, I get ux cosine theta. Where do I go? Okay, plus uy sine theta I hat plus minus ux sine theta plus uy cosine theta j hat. Okay, and this is equal to ux hat I hat plus uy hat j hat. Okay. All right. And so from here we can form a system of two equations, right? Because we have one term with I hat. Okay. Okay. And so we have this expression right here. And so that's going to form one equality condition. Okay. And we can form another equation with the j hat terms. Okay. And so if we put those two equations on top of each other, we can form a matrix set of equations. And so that matrix set of equations is cosine theta, sine theta, minus sine theta, and cosine theta, ux, uy is equal to ux hat, uy hat. Okay. Right, and then we're going to box this equation right here. Right, and so the key to this whole operation here is this matrix right here, okay? And this matrix right here is known as our transformation matrix. Okay, and so basically this is the matrix that we can use to transform between the local coordinates and the stationary coordinates. All right. And so the next thing that we're going to do is we're going to take this transformation matrix and use it to transform our element stiffness matrix for our truss element. Okay. All right. Any questions on this? Okay. All right. People still writing down. I'll give you a couple more. One more minute. Okay. All right. And so next step. Use transformation matrix to express stationary coordinates. Okay. All right. Because right now what we have is something like this, right? So let's say that we have a truss element, and let's say that it's angled arbitrarily, right? And so let's say that we've rotated by an angle theta. Okay. And so if we use the local coordinates, we can form the element stiffness matrix, right? And so we call this node 1, node 2. Okay. And so we'll say this is F2, okay, and this is F1. Okay. My iPad would cooperate, F1, okay. And this right here would be U1, U2, okay. And all of these should have hats because they're in the local coordinates, right? And so from this, we can form our element stiffness matrix, right? And so we have F1 hat, F2 hat. This is equal to AE divided by L, 1 minus 1 minus 1, 1. U1 hat, U2 hat. Okay. All right. And so if we're only looking at this truss element here, you know, this would be fine. But, you know, if we wanted to relate this to a different element, okay, let's say that we have another element that's attached to it like this, okay? And let's say that this is rotated by another angle, angle 2, right? Right. Then our element 2 there would have its own local coordinate system, right? And right now, and then we'd have two different elements with two different coordinate systems that we can't really relate to each other, right? Okay. And so this form of the element stiffness matrix, you know, that we have here in terms of the local coordinates, right now is not that useful to us, because if we had elements that were in different orientation, you know, they each have their own. And so what we're going to do instead is, you know, we're going to take this local system element stiffness matrix and formulate it in terms of the stationary coordinates, so that we can all the different elements can be related in the same way. Okay. And so actually, to do that, the first step that we're going to do is we're going to expand this, okay? Because, you know, one thing I should have written here is that these are all the displacements and forces in the x direction, okay? We also have displacements and forces in the y direction too, right? And so if we do F1y, F2y, okay? And we have U1y and U2y as well. Okay. All right, and so if we take this this local element stiffness matrix and expand it, okay, expand in the y direction, you know, we would have the following. Okay, and so we have F1y or F1x, sorry, F1y, F2x, F2y, okay, and all of these would have hats. This is going to be equal to AE over L times 1, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And so I basically seeded this with a bunch of zeros to account for that y direction. Okay. Because remember, the truss element, it can't actually deform in that local y direction because we're limited to just extension and compression, which is in the local x direction. But we need to have the y directions in there so we can apply our transformation matrix. Okay, so this is going to be U1x, U1y, U2x, U2y. Okay, all of these with hats. All right. Any questions on this, on how we've expanded that system and kind of the reasons why we're doing that? Okay. All right. And so you know, we're going to do two things now, right? And so we're going to take basically this vector right here, which is all local stuff, and then this vector here, which is all local stuff, and we're going to transform that using our transformation system that we have on the previous page. Okay. All right. And they can both be transformed in the same way, right? And so if we have f1x hat, f1y hat, f2x hat, f2y hat, okay? And so we want to transform this eventually into f1x, f1y, f2x, f2y, okay, without any hats, okay. And to do that, we're going to apply our transformation matrix, okay. But our transformation matrix here, we have to expand it too, because our transformation matrix from back here, you know, we only did this for a set of one node, basically, right? And so we're doing a transformation of two nodes at the same time, okay? And so the way that we're going to do that is we're going to make sure, let me draw in the columns as well. Okay. And so to do that, we're going to make sure that, you know, when we transform these guys, they correlate with these ones, okay? And so I'm going to make the transformation matrix like this, okay? And so I'm going to use shorthand just because it's going to be a lot of terms, okay? And so cosine theta, I'm going to shorten as C, and then sine theta, I'm going to shorten as S, okay? Okay. And so we're going to have another entry for the transformation matrix down here, okay? And then we're going to do the same thing for the U's, right? So you have U1x hat, U1y hat, U2x hat, U2y hat. Okay. Is equal to CS minus SC 0, 0, 0, 0, 0, 0, 0, 0, CS minus SC. Okay. Right. And so we have these two transformations here, which we're going to plug in to our expression on the previous page. Okay. Okay. And so by doing this, we're going to replace all of the local coordinates, all the local coordinate terms with the stationary coordinate terms, along with these transformation matrices that are going to come along the way. Okay. Okay. All right, we're almost done, I promise. And then after that, we'll do a couple of examples. Any questions on this? Question? Okay. All right, so let's go ahead and plug those in, and then we'll finish up the derivation here. Okay. And so if we go back here, we can see that on the left-hand side, we have all the f hats. Okay. And so instead of that, we're going to plug in C S minus S C 0, 0, 0, 0, 0, 0, 0, 0, C S minus S C. Okay. And this is now F1X, F1Y, F2X, F2Y. Okay. This is equal to AE over L times 1, 0 minus 1, 0. So this is the element stiffness matrix term, and so this one didn't change. Okay. Okay. And then next to this, we're going to plug in our expression for the U hats, right? So this is going to be CS 0, 0 minus SC 0, 0, 0, 0, 0, 0, CS minus SC. Okay. and then U1X, U1Y, U2X, U2Y. Okay. So a lot of matrices in there. Okay. And so to finally complete the derivation, we're just going to simply take this matrix and multiply it on the previous side, or more like we're multiplying its inverse. Okay. Okay. And then we're going to perform a matrix multiplication of this. One transformation matrix on one side. In the middle, we'll have our element stiffness matrix. And on the other side, we have the another transformation matrix, right? And so we're basically doing a matrix by matrix by matrix multiplication, multiplying three matrices together. Okay. And so I'll spare you the algebra. Okay. And so in the end, what you get is an element stiffness matrix that looks like the following. Okay. And so out in front, we have AE over L. Okay. AE over L is just a scalar quantity. And so it's, it kind of just survives all of this matrix multiplication. Okay. And then inside the matrix, we have a 4x4 matrix. Okay. And so here we have cosine squared, cosine times sine, minus cosine squared, sine squared. Okay, so that's the first row. Second row, we have sine squared, minus cosine squared, or minus cosine sine, excuse me. Okay. We have minus sine squared here. Okay. Then we have cosine squared, cosine times sine, and then sine squared. Okay. And then everything in this matrix is symmetric. And so I'm just going to go ahead and reflect this across the diagonal. Okay, so we have cosine sine minus cosine squared, sine squared, okay, minus cosine sine, oops, minus sine squared, and then cosine sine. Okay. Okay. And so that expression at the bottom, this is your new expression for your element stiffness matrix for a truss element. Okay. And so when we have 2D truss elements, we're going to be using this expression right here. Okay. All right. So that was a long derivation, I know. But after this, we're going to do a couple examples, and then we'll, hopefully using this will be quick. Okay. But even though our expression here for the element stiffness matrix got a lot more complicated, our entire, our usual finite elements solution framework is still going to be the same. And so, if we're presented with a finite element problem, we're going to start by developing the element stiffness matrices. Then we're going to assemble them into a global system. Then we're going to apply boundary conditions, and then we're going to solve. It's just now the process is going to be a little bit more involved because our element stiffness matrices are, are a lot more involved. Okay. Okay. So any questions on this before we do an example?
Yeah, quick question.
Sure.
Or kind of, would you mind drawing in your diagram the directions of F1, F1x, and F1y?
Oh yeah, yeah. So F1x and F1y are just in the, I'll do it in red. So F1x is going to be in this direction. So it's in the pure horizontal direction. F1y is in this direction. So it's in the pure vertical direction. F2x is in this direction. And then F2y is in that direction. Mm-hmm. All right, so let's do an example to kind of show how this is done. So we'll do an example where we just compute the element stiffness matrix for a truss, and then I'll do an example of working it into an actual finite element problem. Okay. All right, so let's assume that we have a truss element that looks like this. Okay. And so let's say that it's angled upwards with with an angle of 30 degrees, okay? Let's see, so with statistics, let's say that its cross-sectional area is 2 inch square. Okay. Its length is 60 inches. And its Young's modulus is 30 times 10 to the 6 PSI. Okay. And so from here, we're just going to take this one element by itself. Let's compute its element stiffness matrix. In the stationary coordinates. Okay. All right. And so before we do that, let's compute the cosine and sine of the angle. Just because it'll make our lives a little bit easier when we're filling in. Okay. And so since our angle here is 30 degrees, if we take cosine of 30, we get √3/2. Okay. And we take sine of 30 degrees, then our S here is going to be 1/2. Okay. All right. And so now that we've computed that, we can go ahead and compute our element stiffness matrix. Okay. And so our element stiffness matrix is going to be 2 inch square multiplied by 30 times 10 to the 6 PSI, all divided by 60 inches, right? And so that's the AE/L factor in front, okay? And we'll see how many of this I can fit in, okay? All right, and so we're going to fill in at least the top half of these terms, and then we can fill in the rest by symmetry. Okay. All right, so let's start in the top left. And so in the top left, we have cosine squared, right? And so cosine squared, we're going to take √3/2 and square it. Okay. Okay. Our next term in the matrix is going to be cosine times sine. And so we have √3/2 multiplied by 1/2. Okay. And the next term in the matrix is minus cosine squared. And so we have minus √3/2 squared. Okay. And then in the last entry on the first row, we have minus cosine times sine. So minus √3/2 times 1/2. Okay. All right. And so you can go ahead and perform that arithmetic, which we'll do a bit later. Okay. All right. So let's go to the second row. And so I'm just going to do the upper half of this matrix because it's symmetric. Okay. All right. And so the next thing we have is sine squared. So sine squared, we have 1/2 squared. Okay. Next, we have minus cosine times sine. And so we have minus √3/2 times 1/2. Okay. And then finally, we have minus sine squared. So we have minus 1/2 squared. Okay. Right. And so we go to the third row. And so the third row, we have cosine squared. And so that's √3 divided by 2 squared. And then we have cosine times sine, which is √3/2 times 1/2. Okay. And then in the bottom right, we have sine squared. So that's 1/2 squared.
I got a quick question.
Sure.
Is it the top rightmost element S squared?
Top rightmost should be minus cosine sine. Oh, sorry, I wrote that wrong here. There's so many elements, I always write it incorrectly. Yeah, so this should be minus cosine sine. I think I was looking at another row accidentally.
Okay, thank you.
Yeah, sorry about that. Yeah, so the top right should be minus cosine sine. Yeah, thanks for catching that. Okay. Okay. And of course, this matrix here is symmetric, and so it'll be, used for reflective problems. Okay. All right. And so the end of this example here is just, you perform all the arithmetic, you perform all the calculations. This factor in front here, this is just a constant factor, and so this multiplies through to everything. Okay. And so it's not the most exciting thing in the world, but it is tedious. And so I have to warn you that, for these problems, I think the main difficulty is not really in the conceptual stuff. It's just in the tedium of the calculations, and just being disciplined with everything, because it's with so many arithmetic calculations, it's so easy just to make a small mistake that just messes everything up. And so, for the homework I'm working on for you guys, I made probably, half a dozen of those today, and and it just drove me crazy. So, it's yeah, it's not these problems aren't the most. I'll tell you, they're not the most fun in the world, and so even I don't really enjoy them all that much. But they are important to know for understanding the theory of finite elements. Okay. All right, any questions on this before we do another example with that is a full finite element problem? Okay. And so this, what we did in this example here, this is kind of just step one of doing a full finite element problem, right? Because, usually what we do is after we form our element stiffness matrix, then we form the element stiffness matrices for all the other elements and work those in together. Okay. So let's do kind of a full problem and see how that whole process works out. And in fact, I'll even throw in a spring in there. Okay. All right. So let's say that we have a 3-element system. Okay. And so let's say that we have one truss element that goes vertically downwards like that. Okay. Let's say that we have a spring element that goes like that. Okay. And then let's say we have one more truss element that goes like that. Okay. We'll assume that this entry right here is pinned. This entry right here is also pinned. And this entry right here is pinned. Okay. And so we actually only have one node in this entire assembly that can move. Okay. And so this node right here is we'll call that node 1. We'll call that node 2. We'll call this node 3. And we'll call this one node 4. Okay. The angles here, we'll assume that this angle right here is 45 degrees. This angle right here is 45 degrees. Okay. This element here is element A. The spring we'll call element B. And the other truss element we'll call element C. Okay. And the load that we're going to be applying on this is we're going to be applying a downward load on node 1. And it'll have a magnitude of 10,000 pounds. All right. So let me go ahead and write the stats. Okay. And so let's say we have a Young's modulus of 30 times 10 to the 6 psi. Okay. We have an area of 2-inch square and a length of 120 inches. And these stats right here are going to apply to both of the truss elements. And so this is going to apply to both elements A and C. Okay. Whereas element B will have a spring constant. Okay. So we'll call this KB. And so we'll say that KB is equal to 250,000 pound per inch. Okay. All right. And of course, nodes 2, 3, and 4 in this configuration here are fixed to the wall, and so they're not going to move. Okay. And so in this problem, what we're interested in is we're interested in the deformation of node 1. Okay. All right. And so this is kind of our first taste of a full finite element problem in 2D. Okay. And so we're going to go through the same process that we've done before. It's just that now our element stiffness matrices are going to be a lot bigger because they're in 2D. Okay. All right. Any questions with the with the problem setup here?
Would we need the springs displacement?
What do you mean the displacement?
Kind of like how much is, no, that's what we're trying to figure out.
Exactly, right. So we're going to be solving for that displacement. So depending on what the deformation here is at node 1, that's going to tell us how much the spring is deforming. Yep. All right. And so here we have, we have 3 elements here, and they're all in 2D. And so let's start just like we always do with these problems, with forming the element stiffness matrices. We'll start with element A. Okay. All right, and so since we're in a 2D configuration here, we have to start out by listing out what is the angle at which A is rotated. Okay. So that's going to be theta A. And so if we, if we start from a horizontal line right here, right? And so we start from the kind of the classical X direction like this, okay? In order to get our element A into that configuration, we would have to rotate 45 plus 45 degrees, which is 90 degrees in total, okay? Right. And so whenever you have a vertical element, the angle is going to be either 90 degrees or it's going to be 270. Okay. In this case, it's 90. Probably next time we'll talk about cases where you would use 270 for that. But for now, we'll just use 90 because it's that's what it is here. Okay. All right. And so let's compute the cosine and sine of 90 degrees. Okay. So cosine of 90 we know is 0. And sine of 90 we know is 1. Okay. All right. And so let's go ahead and form the element stiffness matrix. Okay. All right. All right. So first thing we're going to do is we compute AE over L, which is the stiffness constant for a truss. Okay. And so our A here is 2 in square. Our E here is 30 times 10 to the 6 psi. Okay. And so I'm going to shorten that to 30 E6 psi. Okay. And our L here is 120 inches. Okay. And so if you perform this arithmetic right here, this computing this number will give you 5 times 10 to the 5th pound per inch. And so that's the factor out in front. And so next we have the entries in the middle here. Okay. All right. And so if we go back to our expression here, whenever your angle is either 0, 180, 90 degrees, or 270, this simplifies a lot because remember, the cosine of 90 is 0. And so everywhere here that we have a cosine, we're just going to fill in a 0 there. Okay. And there's a lot of cosines in this expression here. Okay. Right, so the first top left term, we have cosine squared, and so that's just going to be a 0. Next, we have cosine times sine, which is going to be another 0. Next, we have minus cosine squared, which is going to be another 0. And then we have minus cosine sine, which is another 0 right there. And so I'll show you a trick that I use when forming these to kind of save you on about half your work. Okay. So remember, these element stiffness matrices are symmetric, right? And so that means if you transpose it, then you should get the exact same matrix. Okay. And so what I like to do is that whenever I finish writing a row in the matrix, and so usually I start with the first row, I then take that first row and then write it into the column as well. Okay. And so since our first row was all zeros, that means our first column is going to be all zeros as well. Okay. Okay. right? Because for a symmetric matrix, these two entries have to be equal. These two entries have to be equal. And these two entries have to be equal as well, okay? And so as you're building up these 2D element stiffness matrices, go do one row and then write that row into the column as well, okay? I'm gonna get rid of these arrows just because I'm gonna write something there. Okay. All right, I'll show you how I do it again on the next line, okay? All right, so for the next line, we have, the first entry here is sine squared. And so sine squared is gonna be equal to 1, okay? Next, we have cosine sine or something, right? And so that's going to be 0 because our cosine is 0. And then finally, we have minus sine squared. So we have minus 1, okay? Right. And so once again, we've completed a whole nother row. And so let's go ahead and write that row into the column, okay? And so in that second column, the only entries we're missing are the third and fourth one. And so this guy's going to go here. So it's going to be 0. And this guy's going to go right here, which is going to be minus 1. Okay. It's a little disorienting at first. And so, I think kind of the tempting thing is to just go from this equation here and just write out all the terms and compute all these. But when you're doing a lot of these, it saves a lot of time if you just kind of go first row, first column, second row, second column, third row, third column, and so on and so forth. And then you just have that last one right there. Okay. All right. And so we go to the third row now. And so we end up with all zeros there and a 0 in the bottom one. And this is just going to be 1 right here. Okay. All right. And so let's mark out the nodes that this acts on. Okay. And so since this acts on nodes 1 and 2, it's going to be U1x, U1y, U2x, U2y. Okay.
So, Professor, the negative signs inside of our matrix that refer to minus c cosine squared or minus sine squared, that negative applies to after we square
Exactly.
the number that goes in there. Okay.
Yes. Yeah. That minus sign is outside the square. Yeah.
Okay.
Mm-hmm. Okay. All right. Any questions on this? Okay. All right. So that's element A. So now let's do element B. I'm gonna go a little bit faster for this one. Okay.
Sorry, just a quick question.
Sure.
So why is it that we're applying the transformation matrix if based on the forces it's just going to be kind of like extending down, or would it still be rotating it's connected to BNC?
Yeah. So you're right. So you're right. For this one, it would be tempting just to say that, this node right here is probably just going to go vertically down that way. But because we have these elements here, then they're going to be applying forces in their respective directions as well. And so we might actually have some displaced deformation in the x direction too. And anyway, even if we wanted to find the displacement in this direction, we'd have to transform everything here to the stationary coordinates anyway, because this spring here is kind of slanted up by 45 degrees, and this element here is horizontal too. And so we want to get everyone into the same system so that we can kind of compute everything at the same time. Yeah. Mm-hmm. Mm-hmm. All right. So for element B, our theta is 45 degrees. And so cosine of 45 degrees is √2/2, and sine is √2/2. Okay. All right. And so for KB, remember B, our element B here is a spring. And so what we're going to put in front is the spring constant. Okay. And so remember the spring constant was 2 times 250,000. And so if we put this in kind of scientific notation, it's 2.5 times 10 to the 5th. Okay. Right. And just because we're a little short on time, I'm going to go ahead and just fill this in pretty quickly. Okay. But you can go ahead and verify this at home if you did all this multiplication. Okay. Okay. Right, and so if you go through the first row and first column, that's what you get. Okay. Next, I'm going to do the second row, and so the second row we have 1/2 minus 1/2 minus 1/2. Okay. This is minus 1/2 minus 1/2. Okay. Next, we have this row, which is 1/2 1/2 1/2. Okay. And finally, we have 1/2 here. All right, so element 2 or element B here acts on nodes 1 and 3. And so we have U1x, U1y, U3x, U3y. Okay. All right. So that's element B. Okay. Element C, we have a angle of 0 here. Okay. And so cosine of 0 is 1, and sine of 0 is 0. Okay. And so here we have kind of another nice case as well. And so if we do AE over L in front, we have a 5 times 10 to the 5th. Okay. Okay. And so that's the first row in the first column. Second row is going to be all zeros. Okay. Third row, we have this. And then last row, we have just a 0 down there. All right. And then element C here is going to act on nodes 1 and 4. So we have U1x, U1y, U4x, U4y. Okay. All right. So those are the 3 element stiffness matrices of our system here. And so the next step that we're going to do is assembly. Okay. All right. And so this is where, you know, it's going to be a little bit hard to kind of keep track of everything, just because it's you know, we have 8 total unknowns here, right? So 4 nodes. At each of the 4 nodes, we have two components of deformation. And so our global assembly matrix here is going to be an 8 by 8. All right. Any questions on this? Okay. All right. So next we're going to do assembly. All right. And so we'll see if I can fit everything here. Right. And so those are all our columns. And so we have U1x all the way to U4y. Okay. Okay. So we barely fit it. Okay. All right. And so I'm going to do what I did, you know, in previous examples, where I'm first going to basically mark out the sections where, you know, we're going to insert our element stiffness matrices. Okay. So let's start with element A. Okay. And so element A here is working on nodes 1 and 2. And so that's pretty easy. And so we're going to basically box out these 4 rows and these 4 columns. Okay. And so there is our section for element A. Next, let's do element B, which I'll do in blue. Okay. Element B is acting on nodes 1 and 3. And so it's going to be covering this block right here. Okay. This block right here. This block right here. And this block right here. Okay. And then finally, we have element C. Okay. Element C is acting on nodes 1 and 4. And so element C is going to be this person right here. So that part right there is going to be really crowded. Okay. And we have this one right here. This part right here. And this part right here. All right. Okay. And so now let's go ahead and fill in the entries. Okay. And so first, let me start with all the entries that don't overlap, because that's usually the easiest. Okay. And so let's start with element A. So element A, we have 0, 0, 0. We have a -1 in this section right here, but that's going to be -1 times 10 times 5 times 10 to the 5th power. Okay. So this would be -5 E5. Okay. And we have 0, 0, 0, -5 E5, and 0, 0, 0, 5 E5. Okay. I'm leaving that top left section alone because we'll do that last, because that's where all the overlap is. Okay. All right. So next we're going to have the entries from element B. Okay. And so we have a bunch of 1/2s here, but the 1/2s are going to be multiplied by 2.5 times 10 to the 5th. It's going to be 1.25 E5, 1.25 E5. Okay. Oh, all these are minus signs, sorry. Minus 1.25 E5, minus 1.25 E5. Okay. And then same thing over here. And then same thing right here, but these ones are positive. Okay. And then we have the entries from element C. Okay. And so element C, we have a -5 E5, 0, 0, 0. And then we have a -5 E5, 0, 0, 0. And then a 5 E5 here, 0, 0, 0. Okay. All right. And then everything else, of course, is zeros. Okay. It's a little bit messy here, but it is a little bit cleaner than lecture notes. And so if you want to look at it there, then that might be a good idea. Okay. Okay. And now we're going to modify the part where they overlap. Right? And so remember, whenever you have different element stiffness matrices overlapping, then you're just going to simply add together their values. Okay. All right. And so in this top entry right here, we have 5 plus 1.25 E5. Okay. Then we have 1.25 E5, 1.25 E5. And then down here, we have another 5 plus 1.25. So we have 6.25 E5. Okay. All right. And so assembly, nothing's really changed with assembly here. It's just, it's just we're kind of doing it on steroids right now. So it's yeah, it's a doozy. Yeah. And so, when you're doing these kinds of problems here, where you have such a big matrix, I would recommend to use like a program like Excel, or if you're good with MATLAB, you can use MATLAB just to help organize your work. Because most of the mistakes I think that I make too is trying to do these entirely by hand. And then just making kind of a small math error somewhere along the way. And with these problems, if you make kind of a small negative error somewhere here, it's almost impossible to track down. And so, you really want to take your time with these problems and kind of be as organized as you can. All right, any questions on this? All right. All right, and so last thing we have to do before we solve is we have to apply boundary conditions, okay? Luckily for us, the boundary conditions here are very simple, in that, nodes 2, 3, and 4, all of these guys are completely fixed. And so, all of these entries right here are going to be replaced, okay? And so remember, for a constraint, what we're going to do is we're going to put a 1 on the diagonal, okay? And then everything else is going to be 0, okay? So we're going to put a 1 here, turn this into a 0, okay? Put a 1 here, a 1 here, a 1 here, a 1 here, and then everything else is going to be 0. Okay? Someone last year got really upset with me when I did this example because, we spent all this time writing all that stuff down and assembling it, and then we just wiped out most of it with the constraints. So, if you have a little bit of foresight, and so if you can see that, I'm going to knock these out anyway with constraints, you can go ahead and fill that in, and you don't have to do all the assembly. And so, you can feel free to do that as well. Okay. All right. And then our load here, is going to be applied on the in the y direction on node 1, right? And so our load is going to be applied on this row. And so I don't have enough room for it here. But basically what you're going to do is you're going to have a minus 10,000 pounds. I think it was 10,000, right? Yeah, 10,000 pounds in the right-hand side vector. Okay. All right. And then once you've done all of that, you can finally solve the problem. Okay. And so we are out of time, and so I'm going to go ahead and just write the answer down really quickly, okay? And so if you solve it, then all of the u values for nodes 2 to 4 for both x and y, all of them are going to be 0. And so the only non-zero displacements you're going to get are going to be u1x, which is going to be 0.0033 inches, okay? And u1y, which is minus 0.0167 inches. Okay. And so that's the deformation that you have at node 1. Okay. And so going back to your question earlier, Kevin, so you can see most of the deformation here is in the y direction. And so you can see we have about 5 times more deformation in the y, but it does deflect a little bit in the x direction because of the action of the other elements in there. All right, any final questions on this today before we wrap it up for the week?
That top line, is that uz minus 4?
It's 2 to 4. So normally we solve for all the other u's, right? And so all u2x, u2y, u3x, u3y, u4x, u4y. But because of the boundary conditions, all of those are going to be just 0. So that was kind of my shorthand way to say all of those guys are 0. And so that's u2 through 4.
Is that considered a subscript?
It's my lazy subscript. Yes.
Okay.
Yeah, because normally you would say that, u2x is equal to 0, u2y is equal to 0, u3x is equal to 0, u3y is equal to 0. Yeah, so don't do this. You should normally do this. Yeah. So that's what you normally should do, but we're out of time, and so I try to shorten it. Okay, and so that's all we got time for. So thank you everyone for sticking around for a couple more minutes. And so I know today was kind of a lot, but hopefully as we do more examples of these, then these become a little bit less intimidating. Right? So have a great weekend, everyone. Hope everyone stays healthy, and you're staying good. Okay, and I will see you. I'll see you next week.
Thank you,
Thank you,
Professor.
Professor.
Thank you, Dr. Tran. Bye.
Thanks, guys. Have a good weekend.
You too.
Have a nice night.
Sure. I'm meeting with a student right now after class, and then I'll come after that.
I'll be here.
Okay. Yep.
So for your force vectors, everything should be 0 except for your F1 line.
Yeah, F1 correct. Yeah.
For what you have written in green, that's RTS vector.
It's a right-hand side vector.
Ah,
So
right.
it's the forcing vector. Yeah.
Okay. All righty, cool. Thank you, Dr. Tran. Hope you enjoy your weekend and enjoy that wedding. Come back
Thank you.
safe.
Thank you. I will. I'll see you guys on Monday
See you Monday.
or Tuesday. Tuesday for you guys. Yeah. All right, Josh, you wanted to meet after class?
Yeah, can I share my screen with you?
Yes.
If that's all right.
Yes. Let me go ahead and stop sharing. Stop sharing here.
Okay, cool.
Okay, go for it.
I think you have to enable it.
Oh, I do. Yes.
Yeah.
All right, go ahead.
Okay, let me okay, you see my screen right now?
Yep.
Cool. So when I edit the geometry in space claim, so right now I'm doing the wind turbine. I'm pretty sure you know because I came to you before.
Yep.
So I was trying to look at I was trying to make a refinement like at I suppose like the head of the blade.
Okay.
Just because I figured like that's where most of the force is going to be. And so, I was doing a projection view as you have done, or as you showed us in class.
Okay.
But I can't seem to get it on the lower face. Like for some reason, the plane is like super weird. Like it's not, what's the proper word? I guess orthogonal. It's not orthogonal.
It's on the wrong axis. Yeah.
Oh, okay.
This
I
is
see.
not the right one. Hold on.
It's on the axis that is with the base geometry, not the actual fin or blade itself.
I see.
It's the angles that the geometry that holds the blade in place. It's fixing on that.
I see. I see.
Yeah.
All right, let's take a look.
Let me open it up real quick. All right. Okay. So right, like the idea is that I want to make kind of like how I did right here, like a little plane so I can do some refinement.
Right.
I want to do the same thing underneath because it's not just going to hit right here. It's going to hit right here as well.
Right.
So
right.
if I make so I click on this plane, right? Because I want to make a sketch.
Yep.
And if I do a sketch, it's not.
Oh, I see. I see what you mean.
Yeah, right. It's not like
is-
it's not orthogonal to the actual plane itself. It's like a
Right.
little bit curved. And
Yeah.
I was
yeah.
wondering if you knew like if there was a way to mess with it, tweak with it. Because if not, then I guess I could just ignore it and not put a refinement on the bottom portion of like
You can still, and so we
Okay.
can you can either there's a few options here. So
okay.
We can actually use the same plane that you used for the to make that upper part, and we're just going to project it on the lower surface instead. And so let's try doing that first.
Okay.
And so let's go back to modeling. And so I'm guessing your plane.
Delete this one real quick.
Okay.
Yeah.
All right. So where is the frozen body that you used to project onto that thing?
It should be here. I never deleted it. Obviously, it still recognizes it.
Okay.
Right, that little sliver right here.
Yeah. Okay, that's
Kind of
fine. So let's actually just start from scratch. So go ahead and click the top. Just click the top surface.
Yeah, I will.
All right. So then go ahead and let's go to sketching from there.
Okay.
All right. So this is even this is kind of skewed, huh?
Yeah, I was having this issue earlier. Like, I ended up doing it kind of like a weird janky way. So like I would just go back to my modeling and then like delete the plane.
Yeah.
And I attempted that like a couple of times, and I think on like the fourth or fifth time I ended up getting it so that it's fairly orthogonal, like similar to how you showed us.
I see.
In the
I
lecture.
see. Uh-huh.
But that's why I was like kind of weirded out. I'm like, am I doing something that's different?
Okay.
I don't know why it's so.
Yeah, I'm not
weird.
sure actually. I would always think that they would put the plane kind of where the centroid is, but
That's
maybe-
what I
maybe
thought.
I'm wrong.
I don't know.
Okay.
I mean, I could always like restart because honestly, I haven't done much work. I haven't even like really started.
Oh no,
as
it's
bad as that might
you
sound.
can you can keep going. I mean, this is fine. And so we'll basically, so I think the best option might be just to start with one of the XY planes, and then we'll just move it. And so let's go ahead and delete this plane too.
Okay.
All right, so let's click on the XY plane. Let me see. Actually, I think the one that we want is probably going to be XZ or ZX.
ZX, yeah.
Is that? Oh, the whole thing is kind of slanted, huh?
Yeah.
Okay.
Probably
Let's do this. Can you click on the flat top surface of the
right here.
yeah.
Yeah.
So let's go ahead and make a plane off this guy. I think this is fairly close to what we want, right?
Yeah, there you go.
And no, still not really, huh? Okay. So we can modify the plane itself. So go back to modeling and then click on plane 6.
Mhm.
And so you can
Right here, right? Or
fortunately it's all grayed out. I guess it's because you define the plane by clicking on the face.
yeah.
Let's go ahead and delete this one too.
Okay.
And so go ahead to go up to the top left. You see create.
Yeah.
So let's go ahead and create a new plane at the very top.
New. Oh, yeah. New plane.
Okay. And so from here we can go ahead and select a base plane from which to do. Okay.
Okay.
And so do you see in the details view in the bottom left?
Uh-huh.
You see the base plane. So let's change the base plane to X to ZX.
Okay. How do it? Would I just click?
Go ahead and click ZX from the top left in the tree outline.
Okay.
And then click apply.
Okay. There you go.
Okay. And then so do you see the next the next entry? Excuse me.
You
The
okay?
next entry, yeah. The next entry called transform. So right now it's a none, right? So let's go ahead and change that. And so we can rotate this. And so I think we want to rotate it about the Z axis. Rotate
Okay.
about Z. Yeah. Right, because Z. Oh no, sorry. So
No, it would be the
X.
X. Yeah.
Yeah,
the
yeah.
X.
yeah, I forgot they do their own local coordinate system.
Okay.
Okay, and so now you can rotate this. Unfortunately, I don't know what the angle of rotation is for that one. But you can
45.
Yeah, let's try 45.
It's a little too much.
Maybe try 30.
Oh, I think that's it. Yep.
That's the upper plane.
Oh, that's the upper. Yeah.
So let's try
20.
Or it's like kind of midway, huh? Maybe
Yeah.
try 15. That's pretty close, I think.
Yeah. I mean, it's not too bad, right?
Yeah, I mean you can play around with it, but basically once you get the plane actually yeah, it's still not great.
Right.
But you can play around with this. And so do you see now you can add a second transform, and so you can see transform 2 is highlighted there too.
Mm-hmm.
And so you can move this too. And so
Oh, I see.
so you can And so I don't think you don't really need to move it around. Although it might help to move the origin to somewhere that's more convenient. But I think the most important thing is to get the rotation, right. And so you can play with the rotation. It doesn't have to be exact because remember you're projecting a surface onto the
Right.
onto the thing, and so it doesn't have to be exact. But I think it just has to be close enough that you feel kind of comfortable with projecting that surface onto the onto your geometry.
Also, I think I asked you this last time in your office hours on Monday, but so like if you look at the plane, right, it's like not necessarily all the way underneath the I guess I'll just call this the head of the turbine blade.
Yep.
If I wanted to project it so that it's just on the lower half, would it affect the upper portion? No, right? Because
No.
if you're clicking on the target
Exactly.
as right, okay,
Yeah.
just
So
making sure.
it passes through everything except for the target, and then it just hits that target right there.
Okay, cool.
Yeah. So if you want to move it closer, like you can use the transforms to transport the plane, and so you would do offset X, offset Y, or something like that. In this case, I think you'd want to offset in the Z direction. So go to transform 2.
Transform.
Yeah, so you can offset Z.
Z, yeah.
And so you can move it up and down if you want, but I don't think it's going to make that big a difference. But you can do that if you want. But basically, when you project, it's going to pass through everything except for the target point. And so
Too much. Oh God, what did I do?
yeah, you can put it back to 0 if you want. And so use the you see the ruler kind of in the bottom of the middle screen. So use that to kind of give you a sense of how much you should do. You can change the unit system too, and so you can go to units at the top, and probably change it to millimeters. That might be well. I think you might have to click out of this.
Oh yeah, I forgot. Would it be generate to?
Yeah, go ahead and click generate. There you go.
Okay, cool.
Yeah, that might be a little easier, but
Yeah.
But yeah, so if you want to offset it, you can, but I don't think it's not going to make that big a
Yeah, I don't think it's necessary. Okay, yeah, that's pretty much like my main question.
Okay.
I don't know if Steven has a question because I know he wanted to join me just to hear on it.
Yeah, I had similar ideas that I wanted to do with mine because I'm obviously interested in kind of the aerodynamic properties of that kind of stuff, and I was looking to create that when Josh had mentioned that he was having trouble. I tried to help him with it, but I realized I had no idea what I was doing. And so I was like, I want to sit in on your thing. So for the blade, this is kind of like a turbine blade for like an engine, or like not necessarily like a windmill blade.
That's what the place where I got it from. That's what they called it as, but you can interpret this how you want. And so I know one person in the class is basically saying that this is going to be an airfoil, or like the cross section of an airfoil, and then he's going to do basically like he's going to put drag and lift on this thing, which I think is really creative, and so I think that's really cool too. So and so as long as it makes sense and you can kind of explain why you're doing things a certain way, then that's fine with me. So be creative. That's the I'm fine with that.
And you're mainly sorry, go for it, Steve.
Oh no, I was just gonna say I've got like some different ideas. I've been learning a little bit about aerodynamics with senior design and rocket, going over our fins, and there's something called fin flutter that happens when you're at really high speeds, to the point where it can actually rip your fin right off your rocket. And so I was curious to see other types of forces I could put on it, like a drag force. The shape of this definitely induces a little bit of that lift and drag over the top or whatever, but it would be interesting to see, to me, like if I was to simulate like a high pressure or low pressure of that lift and drag, would that be like more of like a distributed load across, say, like the lift would be from underneath, from the high pressure pushing up along that entire surface, right?
Yep. So I would probably do it as a pressure differential. And so you'd have one pressure, a lower pressure up top and a higher pressure on the bottom.
Yeah. Okay. And then I don't need to simulate any kind of fluid flow over it in order to get that. It's just a straight
Yeah, just a straight
pressure for
pressure.
that scenario.
Yes.
Okay.
Yes.
Okay.
Yeah. Yeah, so
And then
it'll,
if I
so
was-
it'll be an approximation, and so like one thing you can do is you can compute, you know, what you expect to be like an overall lift coefficient for this, and then
Okay.
translate that into like as like a net force in the high in the vertical direction.
In the vertical.
That's how I
Okay.
read it. Yeah.
Okay. And then if there was going to be like, I thought about like potentially like a bird strike or some type of thing like that. And your isolated circle or, you know, geometric shape on top of the fin kind of works to simulate that
Yep.
impact strike. Now, it's sort of like an instantaneous thing. So we'd be analyzing the stress as the bird struck, not like over time.
Right. Yes. So it'd be a static simulation. So you
Okay.
basically doing kind of the instant of impact.
Okay, good. Yeah, I think that's all.
Just one more thing from me.
Mhm.
So when it comes to grading, because I know like this project or this midterm project, whatever, is pretty like open to interpretation, and it's, you know, you do as you please, I guess you could say.
Yep. Mhm.
When you're grading, are you mainly looking for like the logic behind our setup?
Exactly.
And
Yes.
essentially, right? Like that's because I'm just wondering, like, how would you base the grading off of like different I guess you know, different like homework like I don't know, just different assignments basically. Like everyone's doing their own thing.
Yeah. So basically what I've been looking for is the logic behind your finite element decisions. So you know,
Okay.
how you chose to, I mean, first of all, you know, kind of like what we're talking about right now, like how you're going to choose to model the loads, like where are you going to put them? Like, does that
Right.
make physical sense? You know, when you're
Okay.
going to the meshing, like does the meshing settings that you chose, does it make sense, right? Did you have
Okay.
refinement in the areas that make sense? Like, did you use the right element order, element size?
Right.
And you know, and for the results, you know, I'm looking to see if you are informative in the results, and so you should be able to explain basically everything that you're getting. And so I don't want to see you just plop a bunch of screenshots from ANSYS into your report. And so I want you to be able to interpret what you're seeing and explain to me, you know, what I'm seeing in these figures.
Okay.
But I want you to be judicious too. And so I want you to basically, you know, I want you to choose what you think is the most important results for your project. Because I think what, you know, when you first, I think, start out, I mean, and this goes for everybody. So I think when everyone's first starting out with finite elements, there's a tendency to just put in just everything. And so just take just a bajillion screenshots and just list everything out there. But, you know, in reality, like no manager is going to have time to read through all of that, right? And so they want you to be judicious about, you know, what's the view or what's the screenshot, what's the angle that shows me, you know, the most information as possible, right? And so those are the kinds of things that I'm going to be looking for.
Okay. Cool. Yeah, that's pretty much it on my end. Thank you for taking the time to meet with me.
Yeah.
I appreciate it.
Glad it was helpful.
Yeah, definitely.
Thanks, Dr. Tran.
Yeah.
All right.
You have a good weekend.
You
Thanks,
too.
you too. All right, see you guys.
See ya.
Yep.